Okay, continuing on. You probably noticed a little difference in the previous videos. This is a kind of a redo of a video I'd done earlier, and someone told me I'd made a mistake. So I'm kind of fixing the mistake I made. Okay, so let's screen share and see what our problem is going to be. And there's the problem that we are going to work on. So we've been looking, or not the problem we're going to be looking at, but continuing looking at limits at infinity as x goes to infinity or negative infinity. So we looked at them charts, we've looked at them graphs, and those are great ways to kind of get a feel for what's going on. And graphs are particularly a good way to understand, or particularly a good way to check answers. But neither graphs nor charts are the ways that you should come up with an answer. You need an analytical method to get an answer. So that's what we've got here, limits at infinity analytically. So if R is positive rational number and C is any real number, then the limit as x goes to infinity of C over x to the R equals zero. Further, if x to the R is defined when x is less than 0, then the limit as x goes to negative infinity of C over x to the R goes to 0. What this is saying in in very fancy language, cutting it down so it's not so fancy language, it's saying this: limits of the form constant. That's the C in both of those. Over plus or minus infinity go to 0. If we allow ourselves to think about substitution just for a moment, and we really shouldn't substitute infinity because substitution is for numbers and infinity is not a number. But now that I said don't think about substitution, let's think about it anyway. If I take this guy here as x approaches infinity of C over x to the R, if I plug in infinity, it's just a fact that as x goes to infinity, whatever you do to it exponent-wise, any exponent you raise it to, R being a positive exponent here, it's still at infinity. The square root of infinity goes to infinity. Infinity squared goes to infinity. The cube root of infinity goes to infinity. So if I think about substituting in there, I would have a constant over infinity that always goes to 0. Then this is taking care of less of going to negative infinity. And all it's doing here is if this is defined. Remember, we aren't using imaginary numbers in this class. And so if I'm going to negative infinity and my exponent is 1/2, that'd be the square root of negative infinity. Well, that'd be imaginary numbers, and we aren't doing that. So this is they're just covering our mathematical rear ends by saying that making sure this is defined. But suffices to say, anything of the form constant over plus or minus infinity goes to 0. So now that we have that new little fact, we can do some problems. And so here's our first problem here. Evaluate the limits. Everything you know about limits is still true as we go to infinity, meaning we can split up limits by adding, subtracting, multiplying, dividing. So what we can do on this case, and that says that up there, all limit laws stated earlier are true when the limit as x approaches a is replaced by limit as x approaches infinity or limit approaches negative infinity. Everything's still true. Primarily, this is still true, that I can split this up into 4 separate little limits. That's supposed to be a 5, not an x. Bring out the whiteout. Then, like I said, everything that you know is still true. So the limit as x goes to infinity of 3 is still 3. The limit of a constant is still a constant. The same thing here. The limit as x goes to infinity of 4 is still 4. then both of these guys, we'll put a little asterisk here, both of those are of the form constant over infinity. And they go to zero. That if you allow yourself thinking substitution, and we shouldn't do substitution, but do it anyway. If we allow ourselves to think substitution, we have that new form, constant over infinity, and constant over infinity go to zero. And so we get a final answer of 3/4. That's all there is to that one. Now this next one is doesn't involve my new form, constant over infinity. This isn't the correct form. So this guy, not in the form constant over plus or minus infinity. And so I've got to do something to get it in the form. So to rewrite, we will divide all terms by x to the highest exponent. Just barely got it on the screen there. So let's rewrite this a little bit. I'm going to try to write small so I can get it all in here. That's 2 plus x to the 1/3 over 3 minus 4x to the 1/2. So my highest exponent there is x to the 1/2. So I'm going to divide everybody by x to the 1/2. So 2 over x to the 1/2 plus x to the 1/3 over x to the 1/2 over 3 over x to the 1/2 minus 4 over x to the 1/2 over x to the 1/2. So I divide everybody by x to the highest exponent, and then I simplify, remembering that in fractions, when I got the same base and different exponents, I subtract my fractions. So simplifying this, I've now got the limit as x goes to infinity, 2 over x to the 1/2 plus 1 over x to the 1/6. 1/2 minus 1/3 is 1/6. And then that's going to be 3 over x to the 1/2 minus 4. And now all of these guys, we'll put the same little asterisks. They all have the form constant over infinity. If I allow myself to think substitution and I replace all those x's with infinity, they're all going to have that form constant over infinity. And so they all go to 0. And so I have 0 plus 0 over 0 minus 4 for 0 over -4 and -4. So the real key to this one was doing that trick of rewriting so I could achieve that form I know. That the only analytical form you know that involves infinity is a constant over infinity. And so to achieve that form, I divided everybody by x to the highest exponent, did my simplifying, and I got my form. Okay, so moving on a little bit. Notice down here, we're going to have to do some funky rewriting on this one, but there's going to be a little more funky rewriting that we're going to have to do. It's going to require a little bit extra thought process. So before we get to that one, we introduce or reintroduce something were told once upon a time, but you probably don't remember that you were told. The square root of x squared formally is the absolute value of x. Now, back when you were studying algebra, you were probably just told the square root of x squared is x. And what you probably didn't notice is in the textbooks, it then said, comma, x greater than or equal to 0. Mathematicians have decided that they want the square root function to be indeed a function. When something's a function, that means there's always, you put one number in, you get one answer. We never ever say that the square root of 9 is -3. Even though -3 quantity squared is 9, we never say the square root of 9 is -3. We always want square roots to be positive. So mathematicians have decided officially that the square root of x squared is the absolute value of x. We just accept that. Then absolute value has an official definition. And here's the official definition of absolute value. The absolute value of x is negative x if x is less than 0. It equals x if x is greater than or equal to 0. And so what this is saying is if I have absolute value, the way you get the answer is if the answer is already positive. If you're inside, not if the answer. If the inside of your absolute value is already positive or equal to 0, greater than or equal to 0, you just use that inside. Absolute value of 2 is 2. You just use the 2. But if the inside of your absolute value, if the argument of your absolute value is already negative, the way you're going to get the absolute value is to take the opposite of the inside. And that looks really bizarre, but think about it for a moment. It actually works. I want the absolute value of -3. And so you were just told long ago, absolute value makes everything positive. And it does. But here's the official definition in play. So that inside is negative. So we fall into this category. If x is less than 0, my inside is negative. So we fall into this category. And so what the rule says is put down a negative, so that's this negative, followed by whatever the inside is. So the answer technically is -3, which is 3. Now we're going to want to remember this when we go into the next problem, that if the inside is negative of my absolute value, the way you get the absolute value is to take the opposite of whatever the inside is. If my inside is already negative, my inside is -3. The way I get the absolute value is to take the opposite of the inside. The two negatives cancel, and in this case, we get 3. That's where we'll end this video, and on the next and last video, we'll do this problem, and that will be the end of these sections. So, ending this video. Bye for now.